All right, so this brings me to our last algorithm within decomposition methods, and this is qubitization and quantum signal processing. This is, I would say, by far the most abstract and involved algorithm of the ones that are presented here. So again, I will give this more or less high-level overview here, followed by a more detailed overview, and then I'll go into a derivation of certain steps of this algorithm, okay? If any of this, again, is too technical for some of you, skip ahead a few minutes. And also have a look at some of these references that are at the bottom here for a more detail and maybe a more comprehensive introduction, okay? So generally the idea of qubitization is to block encode some operator, so some operator A, we call it, into a larger operator. And as an example, this is achieved by such a controlled operation, for instance. So a controlled operation of A on some other ancilla is a block encoding. So just as an example, so you have a visual of this. And qubitization does this in a specific way, which will become more clear later in some derivations. And with this special block encoding, you can then go and perform quantum signal processing on this block encoding, which is this second step here. And essentially with a series of rotations applied to this block encoding, you then successively transform this block encoding into a block encoding of a polynomial function of your operator that you initially block encoded, okay? So takeaway here, block encode some operator that you wish to transform and end up with a block encoding of some polynomial function of that operator, okay? Now, this is extremely versatile and is generally just a transformation into a polynomial of some operator, okay? And you can envision using this as a subroutine in many different algorithms. Crucially, the way that quantum signal processing works is there are some strict requirements on the form of these polynomials. And so eventually, regardless of the function that you want to implement here, you always first have to expand it as a series of polynomials and then decompose these polynomials into polynomials that satisfy the requirements of quantum signal processing, okay? On the example of quantum dynamics or Hamiltonian simulation, you have such a function which you want to encode, okay? And so you can approximate this with as a sum of two polynomials, which turn out to be of the kind that you can implement with quantum signal processing, okay? And we'll see this on the next slide. Specifically, it's special polynomials called Chebyshev polynomials, which end up in here. Once you have these block encodings of both of these polynomials, then through quantum signal processing, you can use your LCU again to combine them, okay? So here, U1 implements the block encoding of F1, U2 implements the block encoding of F2. And so what you end up with in the circuit is applying this sum to your initial state phi, okay? Which is what we want for to implement quantum dynamics, okay? This is the rough idea. A bit more specifically, so I told you, you do this transformation of your block encoding into a polynomial of special kind. You achieve this with a series of rotations applied before and after this block encoding. And the way that this algorithm is constructed achieves an optimal scaling of gate cost, provably optimal, as this is the scaling of the gate cost is linear in t, so your simulation time for the case of quantum dynamics simulations, and also the logarithm of 1 over epsilon, where epsilon is your accuracy of the simulation. Okay, why is this optimal? Because it's linear in t, and it cannot go sublinear in these algorithms, and it's additive here. So it's not multiplicative, but it's additive, which is the optimal scaling law that you can find for Hamiltonian simulation. And on top of this, you do require some ancillas, but these ancillas are constant with respect to the simulation time and the accuracy. Okay, so maybe you think, okay, but we had a similar expression for the number of ancillas with a linear combination of unitaries, and I was telling you it's bad in that case. The thing is that in LCU you had something like this, okay, where you also had this log L, where L is the number of Hamiltonian terms, but more importantly, you had this K here, okay, and this K is the or in LCU is the truncation order of your Taylor series, and this is dependent on the accuracy of your simulation, okay. So in LCU, your number of ancillas depends on the accuracy of your simulation, whereas in qubitization, it does not. It is independent of simulation time and accuracy, okay? And that's the crucial part here. Okay, so then for Hamiltonian dynamics, the way that you implement these polynomials is you expand your time evolution operator as a series of polynomials, and specifically for this expansion you use these Chebyshev polynomials. So, sorry, a bit ugly. These Chebyshev polynomials for a reason that will hopefully become clear at the end of this overview after some derivations, and also these Bessel functions here, okay? And with this you can essentially split this polynomial expansion of this exponential into an even sum and an odd sum, okay? Which both of them you can implement with this block encoding, okay? And then in the end, as I said, you have one block encoding for this even sum and one block encoding for this odd sum, and you combine them with this LCU technique, okay? So far, so good. So let's do some derivations and actually see how to do this. Be aware that most of these derivations might not immediately become, or it might not become immediately clear why they're connected to quantum dynamics or Hamiltonian simulation, okay? And the reason for this is that I will first go into some detail of this block encoding, and in particular how to construct these transformations, okay? And so since this is general and does not only apply to Hamiltonian dynamics, it might not immediately become clear why we have to do this, okay? So just endure through this, and then eventually I'll make the connection to implementing this, okay? All right. So I told you we want a block encoding of our Hamiltonian, yeah? So far we established this. Let's use a different color. So let's say we want some block encoding, okay? And now I would choose a very specific type of block encoding, namely one that looks like so. Okay, so normally it is not important what is written here, it's only important what's written here. But let's just for now, for the sake of being pedagogical, envision such a block encoding. And specifically we have here that H, of course, has an eigenvalue decomposition. So you have the sum of eigenvalues, all eigenvalues of the Hamiltonian times these projectors onto its eigenstates. And then I define this weird square root of 1 minus h squared to be a very similar decomposition, namely 1 minus each eigenvalue squared under this square root times, again, this projector, okay? Oops, I noticed that I used a J here. Sorry for that. It was supposed to be an I in all cases, okay? So, just one index for all of these. Okay, so far so good. And so we can write this W a bit differently, namely as an identity on an ancilla times H minus I times Y, so the Pauli matrix on this ancilla, tensor this square root operator that I just defined, okay? And so what this gives us is that we learn for each eigenvalue of H, we can have the following, namely W applied to a zero ancilla state tensored with this eigenvalue is yields the following. And W applied to the one state, so the one orthogonal to the zero, times this. Oh, and maybe so this, of course, is lambda j 0, lambda j plus. Sorry, I was one step ahead here. So applying this W to this state yields this, okay? And of course, we can plug in our eigenvalues here. I was faster with my head than with my tongue and my pencil. And of course, applying this to the orthogonal state will yield something very similar. With a minus there, times 0. Okay, and from this, it becomes clear that suddenly, if I have this special kind of block encoding, this operator, this block encoding, decomposes into a direct sum of subspaces. Since you see here that for each of these lambda j's, we now have a corresponding block sphere flagged by these ancilla states here, okay? So in particular, W decomposes into this direct sum of SU2 matrices, and so we have a separate block sphere for each lambda j, okay? And this is important here. So we write this down and we see that suddenly we can write this as this direct sum of lambda j minus 1 minus lambda j squared under the square root, and then again here 1 minus lambda j squared and lambda j. okay, times our projector. Which, let's just define this for brevity. Okay, I hope this is clear. But so essentially, if we have n qubit Hamiltonian, then we have 2 to the n eigenstates, and so we have 2 to the n separate love spheres that make up this block encoding, okay? So, oops, I used a little bit too much space here, but essentially, while we focused on this very special type of block encoding now, there is a lemma, so a mathematical statement called Jordan's lemma, which says that any block encoding of an operator, so of H, which is constructed of 2 reflections on the same space, can be transformed into a different basis in which this block encoding has this same structure of a direct sum that I just showed you, okay? So if, or any so we can always find this decomposition, okay? If we construct a block encoding of 2 reflections. And here I think I forgot this. Okay, so far so good. I hope this is all clear so far. So lastly, note that the eigenvalues of this wj are, I'll denote them with this lowercase w, are lambda j plus minus 1 minus lambda j squared, which is equal to the exponential of plus minus I times the arc cosinus, or cosine, sorry, of lambda j, okay? Probably seems completely random to you, the fact that I'm telling you this, but it'll become hopefully more apparent why I'm stressing this in a bit. Okay, so let's go on to quantum signal processing, where we will leverage exactly this fact that a block encoding of 2 reflections can always be decomposed like this, okay? So, alright. So there's one central theorem in quantum signal processing, and it's the following. So In QSP or in quantum signal processing, say you're given a matrix, which we denote by W tilde, and this matrix is dependent on some variable x, which is a scalar, and looks like so. Okay? And this is equal to e to the, I think I have too little space here, equal to e to the I r cos of x times sigma x. And this is a Pauli matrix, okay? So Pauli sigma x. If we have such a matrix, then we can find phase factors phi phi 0 to phi d in some range between minus pi and pi. Such that we can construct a block encoding of our variable x, which looks like so. We call it u tilde of x. And so we combine all of these phases in these phase gates. Again, here the sigma z is a Pauli matrix with a product of applying this w d times, or factoring this d times, together with these other phases, okay? And this will give us this block encoding where px is some polynomial of x, qx is another polynomial, and then in the bottom here we have the complex conjugates. It can maybe be a bit more tidy here. Times, and then px star. Okay? And maybe now you start seeing the connection to what I was telling you before and what I was telling you about the goal of qubitization in quantum signal processing, okay? So remember here, if we have such a matrix, okay, such a block encoding of some variable x, we can transform with this to a block encoding of this polynomial of x, okay? Now, I have not told you anything about these polynomials, and in fact, for this to work, these polynomials have to be of special kind. So for p and q complex polynomials of x and d a positive integer, we have to fulfill the following constraints. So the degree of p has to be smaller than d, and the degree of q has to be smaller than d minus 1, okay? Second, p has parity d modulus 2, and q has parity d minus 1 mod 2, okay? So complicated words, but essentially if you have d equal 4, then p has to be smaller or equal d. So say the degree of p is 4, which means the maximum exponent in this polynomial is equal to 4. And the parity means if it's an even or odd polynomial, so the parity has to be 4 modulus 2, so it has to be 0, meaning p has only even x squared plus x4. Okay, something like this. Vice versa, the degree of q has to be smaller or equal to d minus 1. So say it's 3. Its parity has to be the opposite of that of p, because d minus 1 minus 2 modulus 2. So 3 modulus 2 is 1. So q is odd. For instance, x plus x3. Okay? So nothing more than this, these two statements. In addition, there's a third requirement on these polynomials, meaning that the absolute square of p plus 1 minus x squared, the absolute square of q, has to be 1 for all values of x in minus 1 and 1. Okay? That's it. These are the requirements on these polynomials. All right. But so for these polynomials, you can always find phase angles to construct such an operation that encodes your or let me use a different color here, that encodes your polynomial that you desire. Okay, so this is important. And now what I have to tell you to make the connection is the following, namely this W encoding that I told you about before. So the one that can always be decomposed into the special form that we saw before. So if we have a block encoding like this that can be decomposed into this form, right? Then it's very easy to connect it to this expression, namely that this W tilde of the quantum signal processing theorem is equal to e to the minus I pi over 4 times sigma z times Wj times e to the I pi over 4 sigma z, where again these are Pauli matrices and Wj is of this form as I showed you before. So minus 1 minus sorry okay. Cool. So what do we know now? We can now summarize and see that if we construct such a block encoding of some operator H, the Hamiltonian, which crucially is composed of two reflections, it can always be decomposed into this direct sum structure that I showed you before. Okay, and now if we have, of course we don't have to do this by hand, right, for every eigenvalue, but it's enough that we know if we have such a block encoding, we can, in principle, there exists a basis in which this block encoding has this form. Okay, and this is enough because with this we can now say, okay, we sandwich this block encoding between such rotations to obtain this this transformed block encoding used for quantum signal processing, and then we can use quantum signal processing to construct something like this, okay, where suddenly we encode any polynomial of x. So So if we have such a block encoding, we can always find phase angles to transform this block encoding into one of these special polynomials, okay? And so in practice, maybe if you encode a full Hamiltonian, you will need more than one ancilla, and you will need a bunch of ancillas to encode this Hamiltonian block encode, okay? And so essentially, instead of using these Pauli Z rotations, you replace these by analogous but more general projections, which essentially these pi operators generalize the sigma z to multiple ancillas, okay? You can read up on this in the references. It's very straightforward, okay? So now, since we're on the same page, again, hopefully, if you want to encode this transformation to any kind of function, it's very easy, okay? So you essentially just have to break down your function into polynomials that respect the quantum signal processing theorem. Say, for instance, you have some f of x that you want to encode, and this is a real polynomial. Then you know f of x, you can represent it as the real part of some polynomial satisfying your QSP theorem, and construct this sum of p of x plus its complex conjugate, okay? And so you can find a circuit or phase angles encoding this p of x, okay? Block encoding this p of x. And you can find the circuit encoding this p star of x. And it turns out that it's the same circuit as for p of x, just with negative phase angles, okay? And so what this gives you, I didn't save, but essentially what this gives you is, or sorry, not what this gives you, but if you have both of these circuits, you can again encode them with a linear combination of unitaries, okay? Like so, and here you have u phi, and here you have u minus phi, okay? And your input state, okay? And this gives you u phi plus u minus phi on your input state, which is equal to p of x plus p star of x on your initial state, sort of, because this input state, of course, also includes the ancillas that you need to block encode your Hamiltonian, and this one doesn't, okay? So, and this is equal to 2f of x times phi, okay? So, hopefully this has become a bit more clear. Now, one last thing that I really want to stress is I have not told you anything about how you obtain these phase factors, but it might not be obvious, but it's very simple once you see it. So essentially, you do not have to follow this procedure here with the full Hamiltonian, but it is enough if you do this optimization here in this 2D setting, right? Because then once you can compute the angles from this 2 by 2 matrix calculation, and then implement them with this more general block encoding, but it's the same phase angles, okay? So essentially what you do is you do an optimization, you define a cost function where you want to minimize the distance between this zero projection of your transformation, so the quantum signal processing transformation. The fact that you have to project this on zero is because the zero state will select exactly this element of your transformed or of your matrix, right, of this U. And you want to minimize the distance with the function that you want to implement, okay? And so it's important here that this is a polynomial. Otherwise, this might not converge, this optimization. And in one of the references that I'm going to show you after, a specific way of obtaining this is where these j's here run over 1 to the number of phase angles that you include here, and these xj's are the first d roots of Chebyshev polynomials. Okay, that's very well defined, and it turns out that if you construct it like this, together with an expansion of your target function in terms of these Chebyshev polynomials, then this optimization converges best and gives the best accuracy, right, and stability, which also you can read up on in this reference that I'm going to point out in a second. But essentially here, it's important, this is only 2 by 2 matrices which you have to optimize, okay? And this gives you the transformation of H to f of H if you have a block encoding of your Hamiltonian, okay? Right, so I hope this was clear. So now let me go back to the slides. Specifically, what this looks like is the following. So you remember these prepare and select operators from LCU, and essentially these give you block encoding, and you can use this block encoding for qubitization. So you can check that with this construction here, you get this type of block encoding. And now I told you that in order to do qubitization, we need a block encoding composed of 2 reflections, okay? So we combine it with a second reflection, which we essentially take as this generalized Pauli Z. And if we combine these two, so we take this and combine it here, this new block encoding now has exactly the same decomposition as I showed you before due to Jordan's lemma. Okay. Now, quantum signal processing, very briefly again, if you have such a matrix, you can always find these phase factors to transform this matrix into this matrix, where you here have this encoded polynomial of X now, given that your polynomials P and Q satisfy these 3 requirements, okay? Now, this QSP matrix is related to the block encoding I showed you before very easily by sandwiching it between these 2 rotations. And so using this fact, you can use quantum signal processing as the protocol to transform the block encoding from qubitization into the desired polynomial, okay? So you know how to get this block encoding, you know what restrictions you have on P, so you take some function that you want to implement approximately, say our Hamiltonian time evolution, and you expand it into polynomials that satisfy these QSP requirements, okay? So here this even and odd series of these Chebyshev polynomials. Once you have this, you compute the phases with this just two-dimensional optimization problem, where you optimize here for your polynomials that satisfy the QSP requirements. And then once you have this, you combine these different parts using your LCU circuit. Okay? So that's all in quotes, because I mean it's a lot to handle, I'm sure. But go back to these references; they're very well. They explain this very well. This first one by Low and Zhuang is the original reference of qubitization. The second one by Dong and al. By the Wadey group at Berkeley explains this in a more applied way, I would say, so quite pedagogically. And this third one is an extension of qubitization, kind of, but in introducing qubitization, I think they also do a great job at going through the basics again. So if you have trouble with these two, check this third one, okay? Maybe it'll give you a different perspective. Right, so summarizing, qubitization is a method that gives you the asymptotically optimal scaling for gate counts at a constant ancilla overhead. So the number of ancillas you need is independent of the simulation time as well as the accuracy of your simulation, which is incredible. It lacks a bit of versatility because in its current form, it cannot be used to implement time-dependent Hamiltonians. Although there are works like this third reference that I showed here by Rajput et al. That combine qubitization with product formulas or Q-drift to handle the time-dependent part of the Hamiltonian with this other formula and then implement the rest using qubitization. So yeah, but generally qubitization is an incredible algorithm, as it, I mean, we explained it at the example of Hamiltonian dynamics, but it really just gives this encoding of or transformation of a block encoding into any polynomial of this block encoding, right? And this can be used as a subroutine for many, many different algorithms. And in particular, check out this reference here by Martin et al. On the quantum singular value transformation, where they discuss using qubitization and quantum signal processing to implement different algorithms, including Hamiltonian dynamics, but also others, okay? Like Grover's search and so on. All right, lastly, I want to give a brief introduction to variational methods for quantum dynamics. So generally, we distinguish between equation of motion-based and optimization-based variational algorithms for dynamics. What all of these have in common is that they rely on parameterizing your time-dependent state with some set of variational parameters. They're encoded in this unitary, which is the quantum circuit in our case, and they all are implicitly assumed to be time-dependent, okay? Now, in the equation of motion-based approach, we want to derive an equation of motion which we can then integrate, so a differential equation for the parameters which we can integrate to get the evolution of the parameters, okay? So kind of the pseudo dynamics of these parameters here that then carries over to define the dynamics of this approximate variational state, okay? So for this, we use a well-established classical variational principle. There are three different ones, but here we use McLachlan's principle. So McLachlan, it's been used extensively in classical computing since the 60s or 70s, so it's nothing new to quantum computing, but still we can use it to derive an equation of motion. Essentially what it does is it says, okay, the exact dynamics follows the time-dependent Schrödinger equation, okay? If we now want to model this dynamics with this approximate state here, dependent on the parameters, then ideally this would also satisfy the Schrödinger equation, okay? So in order to find the optimal trajectory of this the state, we want to find the minimum distance between these two terms, which is the left hand and the right hand side of the Schrödinger equation, okay? And this difference is then varied with respect to the parameters to minimize this distance, okay? And so through this prescription, it's very intuitive kind of to think about finding the optimal parameters to minimize this distance, okay? So the difference to classical algorithms, where this has been used for a long time, is that in quantum computers, we can only encode real parameters. And the reason is that that these parameters appear as rotational angles in these rotation gates. So here, for instance, in the RZ gate, okay? So from this condition here, we find an equation of motion for our theta parameters, where we see here theta, the time derivative of theta appears now in this equation of motion, and M is this matrix consisting of these overlaps between different derivatives of the variation of state with respect to all of the variation parameters. And V, the right-hand side, is this vector where we have this Hamiltonian appearing, okay? We can then use some numerical solver, like an Euler solver in the simplest case, or a Runge-Kutta, or whatever you like, to integrate this equation of motion and find parameters at the next time step, okay? So this will look something like your parameters at t plus some time step will be some function of your parameters at t, so at the last time step, as well as inverse of m and v, okay? In this case here. So here you already notice two bottlenecks probably of these kinds of algorithms. First, at every time step of this integration, you need to fill all of these matrix elements, okay? And so there's n squared if n is the number of parameters here that you need to measure, or you need to measure n squared times at least, if n is the number of parameters. So you can imagine that the number of measurements can quickly become very huge. And also, you need to invert this matrix. And depending on the noise of your machine or your system or whatever, these matrix elements might not be measured very accurately. And so inverting this m might be very unstable numerically, okay? Right. So schematically, this looks like follows. You have this parameterized state in your quantum circuit. You measure certain observables in this quantum processor, which you then feed back to your classical computer. Use those to update your parameters and feed the parameters for the next time step. So theta nu back, and so you iterate back and forth until you reach your final simulation. Okay. On the other hand, optimization-based algorithms, they rely on the same thing. They encode the time dependence in such variation of parameters, but they do not require solving or integrating an equation of motion or inverting this matrix that I showed you before, but instead they do an optimization step to overcome some of these issues, okay? So one way to do this, for instance, is you have a parameterized state here, and then to get the parameters for the next step, so say theta prime here, you apply a small trotter step, just one trotter step, right? So circuit of constant depth to your variation of state, and you minimize or you maximize the overlap with this new parameterized state, okay? And so in this way, you try to follow the trajectory, the correct trajectory as closely as possible. Another way to do this optimization-based quantum dynamics is with something called variational fast forwarding. And essentially you try to variationally approximate this Trotter circuit, okay? So this product formula here. And so you try to diagonalize this with such a parameterized ansatz. You minimize a certain cost function to obtain the best parameters here, closely resembling this product formula here. And then because this operator in the middle here is diagonal, you can essentially use the same parameters and just do different number of time steps, but using the same circuit to get your evolution at every time step, okay? So here you do one optimization at the beginning, and then you use the same optimized parameters throughout your entire evolution, okay? In particular, for this variational fast forwarding, though, you need to double your qubit register, so there is some ancilla overhead, which can be considerable depending on the system size that you simulate, okay? Right, so after this brief overview, some pros and cons of these variational algorithms. I mean, generally, these variational algorithms would fall into this near-term algorithm category if you would classify your algorithms as near and long-term, because their target is to model your system with much shorter circuits than these decomposition methods, okay? And so in particular, because you construct this variational ansatz and then use the same circuit for your entire evolution, the circuit depth is constant throughout your evolution, which is a difference to product formulas, for instance, where the depth might grow throughout the evolution. So this is definitely an advantage, okay? On the other hand, as I was alluding to before, they're completely heuristic. And so it's very, very system dependent if you can find a good variational ansatz that will give you an efficient implementation of your real trajectory or real evolution. For some systems, you might be lucky and find that, or you might do an educated guess. For other systems, it might not be possible to do that. And you might end up with an exponentially costly simulation, just as classical simulation, okay? The key here is that you cannot know before you do the simulation because it's completely heuristic and you cannot do any estimates of costs and accuracy with these heuristics or variational algorithms, okay? Another advantage is that it might be easier to do dynamics and first quantization in this approach here, as we discussed in another paper, which I forgot to reference here, but it's by Pauline Olitro, and recently came out on the archive, so check it out if you're interested. So these EOM-based algorithms, because of the facts that I told you about before, they usually require a large amount of measurements, which you can read up on in this paper that we published last year. And so for relevant system sizes, maybe, to compare to classical simulations, these number of measurements are so large that you cannot carry out the simulation because it simply takes too much time to do all of these measurements or to execute all of these circuits, right? And also they can be unstable due to matrix inversion, but this is not as pronounced as this number of measurement problem. With these optimization-based algorithms, the number of measurements is lower than in the EOM-based case, but still for some, this number can become prohibitively large. And also, depending on which algorithm you use, whether you need the small Trotter circuit or you do this variation of fast forwarding, you might need longer circuits and more gates, and possibly also some larger ancilla overhead compared to the EOM based, okay? So take these with a grain of salt. There's always a trade-off, right? So either you do less measurements, but then potentially longer circuits, or you do this more EOM-based, more intuitive evolution, but you might end up with a lot of measurements. Yeah, so this brings me to the end of the algorithms part, and next is some discussion on applications.